Okay, one lesson from chapter 7, arc length. So chapter 7, remember, that's when we found area bounded by two curves, volumes of revolutions, and solids. Okay, so now arc length. Given a function f of x, let it represent a smooth curve. And a smooth curve is just a function that is always differentiable. All right, so that implies continuity, always differentiable. So a smooth curve on a closed function. So then the arc length is the integral from a to b, the boundaries of the curve, square root of 1 plus the derivative squared. Okay, so there's a lot of algebra that goes into this before we even attempt to find the antiderivative. If our function is in terms of y, then we can still find the arc length and we just change it. Now my boundaries would be the horizontal lines, y is equal to d and y is equal to c. Derivative squared, the rule is the same. If you remember arc length from pre-calc, when we found just in a circle, okay, that was our radius times our central angle. Gave us the length of an arc in a circle. All right, so let's look at some examples. All right, so we have a smooth curve, and it is defined from 0 to 1. All right, so I'm going to do the square root 1 plus f prime of x squared. So I'm going to do the algebra behind it before I even plug it into the integral. All right, so first let's start with the derivative. So y prime, using our power and chain rule, subtract 1, multiply by 2x. Okay, so now I have y prime is 2x times the square root of x squared plus 1. Next step, we square the derivative. Okay, so y prime squared would be 4x squared times x squared plus 1. Remember to square every piece of the derivative. All right, so let's distribute that. 4x to the 4th plus 4x squared. And then our last step, we add 1 to the value, to the expression that we got from squaring the derivative. Okay, so let's look at what this gives us. So s will be 0 to 1. We still have to take a square root in order to finish the antiderivative. So let's work with this function algebraically, and you'll see some things are going to start to make sense. So this is factorable. All right, it's a perfect square trinomial, and it factors to 2x squared plus 1 quantity squared. All right, so if you wanted to check that, square the first, double the product, square the last. So now when I take this as my most simplified form of 1 plus f prime of x squared, 2x squared plus 1 quantity squared, now look at how easy the integral becomes. So it's the integral from 0 to 1 of 2x squared plus 1 dx, and now it's just a simple power rule. So 2x cubed over 3 plus x, and we evaluate that from 0 to 1. So 2/3 plus 1 minus 0. So the length of the curve, this smooth curve from 0 to 1, is 5/3. So a lot of algebra before we even get to the calculus part of it. Okay, y is x cubed divided by 6 plus 1 over 2x on the closed interval from 1 to 2. All right, so let's start with the derivative. I'm going to write this 1/6 x cubed plus 1/2 x to the negative 1. No need for chain rule, just simple power rule derivatives. So I get 3/6 x squared minus 1/2 x to the negative 2. All right, so I'm going to factor out a 1/2 here. If I factor out a 1/2, I'm left with x squared minus 1 over x squared. All right, so make some moves algebraically to simplify this before we then go and square it. So I'm going to get a common denominator on the inside. So that gives me x to the 4th minus 1 all over x squared. Now I'm going to square the derivative. So that gives me 1/4 x to the 4th minus 1 squared all over x to the 4th. Not sure if that's going to help me, but I'm not going to square the binomial unless I have to. Okay, I'll square the denominator. Now I'm going to add 1 to it. Okay, so I have 1/4 x to the 4th minus 1 squared all over x to the 4th plus 1. So let me get a common denominator here, because if I think about taking the square root of this, then there's certainly more that can be simplified underneath the radical. So let's expand the binomial, square the first, double the product, square the last. Okay, I already got my common denominator. All right, if I look at my I didn't get my common denominator. So this has to be a 4. And then plus 4x to the 4th. So combine like terms, x to the 8th plus 2x to the 4th plus 1 all over 4x to the 4th. Okay, so if we think about taking the square root of the top and bottom, and be able to take the square root of that. Now let's see if the numerator is factorable. So perfect square trinomial again, x to the 4th plus 1, quantity squared all over 4x to the 4th. So now this is just what goes into the integral. So I'm going to go to the next screen. So s equals the antiderivative from 1 to 2 of the square root x to the 4th plus 1 squared, all divided by 4x to the 4th. So now I can take the square root of the numerator divided by the square root of the denominator, and I get x to the 4th plus 1, all divided by 2x squared. So now, to evaluate the antiderivative, let me break up that numerator. So it becomes x to the 4th all over 2x squared plus 1 over 2x squared from 1 to 2. All right, you can factor out a 1/2 if you want. The first term simplifies to x squared, and then writing this as a power rule, x to the -2 for the second term from 1 to 2. Anything to make your life a little bit easier when you actually have to go and evaluate the antiderivative. Okay, so finish that problem for me. Find an answer. There is another one. I'm going to do another example here, but finish that for homework. All right, so let's start with the derivative here. Smooth curve from 0 to 1. So 2/3 times 3/2 x. Subtract 1 from the exponent. That's not negative. Plus 0. Okay, they cancel. So now when I square the derivative, right, so the derivative just came out to square root of x. When I square that, it's simply x. And then when I add 1 to it, so it's a very easy antiderivative. So arc length will be the integral from 0 to 1 of the square root of x plus 1 dx. Okay, so there's nothing more I can do algebraically, but it just sets itself up for a simple u substitution. So this would equal from 0 to 1, square root of u du. Okay, so antiderivative, add 1, divide by the nu. Nope, didn't do that right at all. Add 1 to 1/2. So u to the 3/2 times 2/3. X plus 1 to the 3/2, and then from 0 to 1. All right, a common mistake that is made when you see zeros abound. Remember that that doesn't necessarily mean that the function goes away. So when I plug in 2, I get 2 to the 3/2. And then when I plug in 0, I get 1 to the 3/2. Okay, so what would I expect for this answer? 2 cubed is 8. We're finding the square root of 8. This simplifies to 2 root 2. So your final answer, these are non-calculator problems, so I would expect to see that as a final answer. So not difficult. All right, one more example. So now we're looking from 0 to 9, okay, and these graphs are in your book, so you don't have to worry about sketching the graphs. You'll get these with your homework. Y prime, 2 times 3/2, x to the 1/2 plus 0. So when I square that, I get 9x. Add 1. So then the arc length would be the integral from 0 to 9 of the square root of 9x plus 1. Okay, another u substitution. U would be 9x plus 1. Du is 9 dx. So my arc length would be 1/9 the integral from 0 to 9 of u to the 1/2. Okay. So complete those two problems for me. Evaluate those answers to find the arc length.